The same thing that makes this happen makes this happen. And this. It's electricity. Whoa.
Bill Nye the Science Guy.
Bill Nye the Science Guy.
Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Brought to you by electrons, making your world a brighter place.
Hey, is your TV on? If it is, that's great. You're using electricity. But if you're watching the show and your TV's not on... Anyway, what is electricity? I mean, where does it come from? Is it just sitting in the wall waiting for us to use it? Or is it constantly spilling out of sockets and we don't notice it? And how can something so powerful be invisible? Well, electricity is the flow of tiny particles called electrons. And they're not just smaller than atoms, they're actually part of atoms. Take a look at this. It's our battery-powered electrical circuit of science. We're going to run this big light with this big battery. Watch.
Attention, Nye Lab.
See, right now, electrons can flow from this side of the battery, through this wire, through the switch, through this wire, into the light, and back to this side of the battery. They're flowing in a closed path, what scientists call an electrical circuit. Now, circuit, that's from an old word for go around. So electrons, right now, can go around an electrical circuit. The flow of electrons is a lot like the flow of water. No kidding. Watch. When I operate this great big water pump of science, water goes through this hose into this box and makes this water wheel go around. And it goes out the other side and through this hose back to the pump. It's a closed path for the flow of water. It's a water circuit. It's just like the flow of electrons through an electrical circuit. Electricity is a very versatile form of energy. The same electrons that are making the light light up are making a motor go around. See, electricity can do all kinds of different jobs, and they're all done with electrons.
Electrons flowing through a wire are a lot like water flowing through a hose. When we got the flow going, we can do work.
Bumper cars have electric motors. The electricity runs from the rod that touches the ceiling, through the electric motor in the car, and then to the floor. So you don't get a shock from the floor unless you can touch the ceiling at the same time. Otherwise, it's not a complete circuit. Sirens!
Keeping batteries in the refrigerator makes them last longer. Your brain uses the same power as a 10-watt light bulb. Cold metal conducts electricity better than hot metal.
Now you know!
There's enough electricity coming out of the wall to stop your heart. So don't stick anything but a plug in a socket. Be careful. This is Godzilla's hairdryer, I think.
Check this out. It's an electric train. It has 2 rails. The electricity goes in one side, through the motor in the engine, then back out the other side. It's a circuit.
So where does electricity come from, anyway? Well, in 1831, two scientists figured out how to make electricity. It was Michael Faraday, working in Britain, and Joseph Henry, working in the United States. And about the same time, they both did an experiment, something like this. Michael Faraday took a coil of wire and he moved it over a magnet. And when he did, electricity started to flow in this coil. The electricity went down over here to another coil and made a compass needle move. Well, Michael Faraday was doing this experiment for an audience, and a woman came up to him afterwards and said, Mr. Faraday, of what use is it? And he said, Madam, will you tell me the use of a newborn child? And what he meant was, would you take a look? I mean, I'm moving the compass needle without touching it. You understand? I have a coil of wire way over here, and I'm making a compass needle move way over there with no apparent force. I mean, some force is going right through the air and wiggling that needle. Something's happening here. Some spectacular effect is happening here. You may not completely understand it right now with no apparent force. One day we will, and it's going to be a big deal. Thank you for joining me on Consider the Following.
My name is Venkatesh Iyer, and I'm a scientist working on electric cars at Western Washington University's Vehicle Research Institute. And this is an example of what we have. This is Viking 21, an electric hybrid car. Viking 21 is the forerunner of electric cars, the way steam engines were to gasoline cars, say. This car is a solar electric hybrid, which means it runs on solar power, electricity, and also on compressed natural gas. There are 1,400 solar cells on this car. Solar cells convert light into electricity, and this is stored in the batteries. And this electricity is used to drive the electric motor in the front and electric motor in the back. The batteries actually are all charged up. So if you guys want to go for a spin, let's roll, let's burn rubber.
Electricity is the flow of electrons. Electrons are the tiny particles that buzz around the outside of atoms. Now, when electrons are able to jump from one atom to another, well, that's the flow of electricity. Now, in some materials, like metals, electrons can jump from atom to atom very easily. Atoms in metals are like a bunch of beehives. The electrons are like the bees buzzing around the hives. When electricity flows, it's like the bees jumping from hive to hive. That's electricity.
You can make an electrical circuit and figure out what things let electrons go through them and what things don't. Hook up a circuit like this.
The tricky part of a circuit like this is getting the batteries to stay put. We've got it all worked out.
Test things and see if electricity goes through them and what things don't. It seems that metal things carry electricity pretty well, and rubber and plastic things don't. Try this, a pencil. Now a pencil slit in half.
Check it out. It changes. The circuit's complete. But the pencil lead is holding some electricity back.
Things that let electricity go through them are called conductors. Things that don't are called insulators.
This can be called a resistor. It's somewhere in between a conductor and an insulator. It lets some electrons go through, but not all. Wild! Wild! Wild!
Uh-huh.
Electrical circuits and water circuits both have pressure and flow. Think about it. Sometimes when you go up to a drinking fountain, the water comes out just fine. But other times, at other drinking fountains, it hardly comes out at all. That's because it doesn't have enough pressure. In electrical circuits, there's pressure too. It's called voltage. The higher the voltage, the more electrons want to jump. Now, the number of electrons that's flowing through a wire we call amperage, or just amps. Now, amps are like the amount of water that's coming out of a drinking fountain. The more amps, the more electrons. So in electricity, we end up with two things: voltage, or volts, and amperage, or amps. Volts and amps. Volts and amps. Volts and amps. The same way with water, we end up with pressure and flow. Pressure and flow. Pressure and flow. Now, the combination of volts and amps we call watts.
What?
Watts. Now, you know about watts. A 100-watt bulb needs more watts than a 40-watt bulb. I mean, it's a bigger number, more watts.
What?
No, watts. Boy, that's a lot of watts. Okay, we're gonna do some power exercising. Ready? And. See, the generator is connected to the exercise bicycle wheel. We're running the generator, that's completing a circuit, and we're turning that light bulb on. It takes a lot of power to run an electric light bulb. It takes a lot of watts.
What?
Watts, electrical power. You see, a 100-watt light bulb takes 100 watts of power. That's a lot of power. That's a lot of watts. Make it burn.
Okay, it's burning. Can we stop now?
Next.
Electrons are pushed by chemical reactions, like in batteries, or they get pushed by generators. Now I need to find someone to push me.
Batteries and hot dogs are a lot alike.
Oh?
No kidding. A hot dog has a piece of meat with a roll around it. Well, inside a battery, there's a long rod with a can around it. Now, between the rod and the can is some goopy chemicals called electrolytes. Now, that's what makes electricity flow. Between a hot dog and the roll are some goopy chemicals called mustard and relish. So instead of poles, it has rolls. Now, if you put a hot dog in a flashlight, nothing happens. Duh. That's because a hot dog doesn't have the right chemicals to make electricity flow. But a battery does. And those chemicals are what make electricity flow from one end of the battery to the other. Now, when the chemicals are used up, the electricity stops and the battery's dead. But batteries are a good, compact source of energy. So are hot dogs. Electricity can be dangerous. There's enough power in a wall socket like this to burn your skin. Just be careful. Hey!
So now it's time to feed our famous electric eel. This is a South American electric eel. It's found only in South America. They can produce up to 800 volts at 1.5 amps. If you were to put your hand into this tank now with the fish, just one hand, your hand would probably fly out when you discharge this main electrical charge. If you put two hands in there, you would probably be electrocuted.
Imagine if you had all this water falling from here down to there, over 100 meters. You could generate 6.5 million kilowatts of electricity. That's a lot of watts.
What?
Grand Coulee Dam in Washington State in the USA. Now, if you've ever lifted a bucket of water, you know, it's pretty heavy. Well, imagine how heavy the water is behind that dam. It's over 100 meters high. It's almost 2 kilometers long. That's a lot of water. So as the water flows from the top to the bottom, it runs huge generators. No, really huge. I mean, big. I mean, very big. I mean, bigly, hugely big generators. 6,949,000 kilowatts. That's a lot of watts.
What?
watts. Electric power. Electric power that runs from here to millions of homes so that people like you can watch television and play video games and pop popcorn in your microwave ovens and have toasted tarts from your toaster in the morning at breakfast. Man, that thing is big.
We use electricity all day. Most of the time, we don't even think about where it comes from. Once it's generated, electricity may travel hundreds of kilometers through power lines before it gets to our homes. Whoa!
When we make electricity with a magnet and a coil of wire, either the magnet or the coil has to be moving. Now notice that the coil is either right side up or upside down. Right side up, upside down. And the electricity that gets made goes this way or that way. This way, that way. We say it's alternating. We call it alternating current, or AC. Now, when we make electricity with batteries, the electricity only goes in one direction. We say it's direct current, or DC. So this is DC, AC, and PC. PC, that's what I call popcorn.
We've known for years that the sun is a wonderful source of energy, but there's things that we need to learn about it. We are trying to gather some information to make photovoltaics more economically viable. Photovoltaic cell is basically just a little tiny cell that you shine sunlight on it and you get electricity. If you ever used one of those handheld calculators, they have a little tiny photovoltaic cell, and basically this is what these are. They're photovoltaic cells, so basically this could drive just one big calculator.
Birds can safely sit on one of the wires on power lines because then their bodies don't complete a circuit. The monsters in science fiction movies, they complete circuits. Ouch!
For electricity to do work, it has to flow in a complete loop. That's called a circuit. Turning on a switch completes a circuit. Turning it off breaks the loop.
Hey, turn on the lights. I can't see. Ooh.
I wish there are no such things as batteries.
Coming this holiday season, a movie that will brighten your spirits.
So, he wants to know what life would be like without batteries. Well, let's show him.
It's one boy's journey into a life without direct current.
Mom, come on, we're gonna be late.
Okay. Oh dear, it stopped.
It stopped. Mom, what's wrong?
Oh dear, it's dead.
What do you mean, it's dead?
The battery's dead.
Hey!
From the director of Compass Man comes It's a Wonderful Light.
Oh, the battery! Hey, Grandpa! Hey, Grandpa! 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 Can you hear me? Grandpa! Grandpa! Hey, Grandpa, how you doing?
I can't hear you.
Grandpa, what's wrong? Your battery's dead?
Can one boy survive in a world without batteries?
These batteries must be dead.
This plug fits in this socket perfectly, but this plug is from Europe, and it doesn't fit in our sockets. No way. See, different countries use different style plugs for their electricity. But notice that they all have 2 prongs. That's because electricity has to flow in a loop. So it goes in one prong through this wire, through an appliance like this blender, then out the other side and back into the wall. It's a circuit. That's good. That is good.
Well, everybody knows that when electrons flow, that flow is known as electricity. And although you might say so, without it, don't you know? Please be unplugged, but not on MTV. Now in a battery, current's called DC. It flows straight from the minus to the plus. But the current in your wall is known as AC, y'all, and it cycles back and forth without a fuss. So don't lose that charge, that AC-DC charge, your current alternating or direct. Cause if you lose that charge, that AC-DC charge, there's no reason for a circuit to connect.
They're beautiful, aren't they? All those electrons flowing through all those conductors in complete circuits. Look at all that light. It's great. It's electricity. Well, guess what?
Real funny, though.
That's the end of our show.
Produced in association with the National Science Foundation.
See? This generator is connected to the exercise bicycle wheel. And it completes a circuit that powers this light bulb. Just a few more minutes. That's it. Breathe. See, it takes 100 watts to run a 100-watt light bulb. Now, 100 watts, that's a lot of watts. That's a lot of power. Power, that's energy per unit of time. You're burning calories. Don't slow down. Make it burn.